looking at lightweighting and cost reduction. So in the automotive space, if we were to look a decade ago, I think that the story was maybe different in that there were opportunities to take, I don't know, an A pillar, you make it a little thinner, change the material, you take cost and weight out. Hey, here's an easy win. Let's move on. But all that low hanging fruit is gone. So I think from my opinion, I think kind of to your points here, the the real improvements and kind of the step function improvements take place in when we're able to take more of a systems view and integrate different components and rethink the architecture. So yeah, that all jives with kind of my understanding of the industry. But I want to dig into how how this composite and aligned fiber approach really works. So maybe starting at kind of the basic level, can you I don't know, for anyone who's not familiar with composites, can you describe, okay, what is actually, how does this material work and how is it different than, thinking of something like an aluminum or steel?
Yeah, so metals are isotropic materials. They have the same mechanical properties in the X, Y, and Z axes, where composites are anisotropic material, which behave a little bit more like the grain of a tree that I think everybody kind of intuitively understands that is not the same mechanical performance in all axes. If you align the grain, you're going to get better performance. So we frequently use the analogy of tree grain, and you can imagine where the branch comes off the trunk of a tree and how the tree grain just beautifully follows the form. And we call that having fiber alignment follow the loading paths or the stress vectors in a part. And doing so is what takes, I think everybody's seen the material data properties of composites that always look amazing. And the question is always, why don't you see them in more complex parts? And it's really because of this problem of aligning fibers with a complex geometry. And that's really where our manufacturing method has developed new latitudes to take these higher performance shapes that haven't been possible to use composites in before, and in fact use the continuous fiber composites in these more complex shapes. Now, just as an example, I'll just hold up here an aerospace bracket. There's a really good example where typically the feedstock that folks are working with to solve problems looks like this, which is just a sheet of laminated carbon fiber composite material. In this case, it could be glass fiber, aramid, a whole variety of composite feedstocks that you can start from. But you can't turn this shape into this form. That's the takeaway. And what's more is this part, the fibers actually run around those fastener holes, down the legs around these fastener holes. And it's really pretty intuitive. If you think about like lashing a boat to a dock, you want to run the fibers around the fastener up here and down the leg as directly as you can around the fasteners down on this end. So, you can really be a pretty good expert on optimizing composites if you think about lashing boats to docks. So that said, that's really what at the most granular level we're able to do to solve the mechanical challenges like strength and stiffness. However, this is intimately related to other functionality as well. You can control thermal aspects, various dielectric aspects of the part as well. And this is where we had to develop software that can optimize for different functional requirements within the same part. And while we can use glass fiber as a antenna window, for instance, which was developed in aerospace within carbon fiber parts as an example. The other thing that you can do is you can embed wire, which, fundamentally, this is a demonstration of wire embedded in a truss to carry, signal, power, electronic things of that nature. And that really gives you a little bit of Mechanicals are where we really started. However, all of these other functional requirements that once you start taking a complex product to market all come into play.